Okay, so this is part 2 of Almost Exact. So we're going to start off with this warm-up, and we're going to solve the initial value problem. So we're going to try to use the method of exact equations first. And let's go ahead and clear a differential. So we do want our dx term, we want this term to be first. And I think I'm going to distribute this. This is m. So this side is in terms of x, so that's 0. Since these are equal, it is exact. Okay, so in order to find f, let's go ahead and start with f of x. To find f, since this is the derivative, we're going to integrate it in terms of x. We're going to add our constant, but since that was in terms of x, our constant is in terms of y. So there's our function that we need. We just need to make sure that we find c of y to complete it. So let's find f of y. So we'll take the derivative in terms of y. F of y is equal to this f of y. So let's write that. Looks like these will cancel. The 2xy will cancel. So we have a winner. Looks like the tan inverse of y. So now we have our function. And our solution, and that's our general solution. It's basically f of x, y is equal to a constant. This is our f of x, y. And there's our particular solution after we found C. So part 2, almost exact. Basically, we have a DE. You go and check to see if it's exact, and it's not quite exact. It's off a little. So what we're going to do is we're going to find a factor similar to the integrating factor that we'll use to multiply through both sides of our DE and then check it for exact, and it should be exact. So part 2, almost exact. So what do we do when we go to test for exact and it's not quite exact? Well, we're going to find a factor that will make it exact. So we're going to find a factor mu of xy to make our DE exact. So remember, when we were finding integrating factor in the last chapter, we were finding mu of x, and we actually even found mu of y on that last example in that section. So mu is an integrating factor, and just like the integrating factor we saw in the last chapter, you multiply both sides of the DE by that integrating factor. So we multiply once we've done that, this is my new M. This is my new N. And then you go and check for exact, and then you do the problem identical to the exact problems we did on the other video and our review. Okay, let's see how we can find this integrating factor. We need my equals nx. So we're going to use our new m and our new n. And we're going to take the partial of it. The left side, the partial in terms of y, and the right side, the partial in terms of the x. So this is where we're going to use our note. We're going to assume mu is in terms of x only because it's easier. We don't have to do the product rule over here. So if mu is only in terms of x and we're taking the partial in terms of y, we do not have to do the product rule. It is just mu. Over here, it is in terms of x, n is in terms of x and y, and we're taking the partial in terms of x. So we do have to do the product rule. U n x plus mu prime n. Well, we're going to isolate this. It's the only derivative that we have. So d mu dx. Go ahead and factor this mu out because I think I am going to be separating this. solve for mu, have to take e of both sides. So mu is e to that integral. So I want to do this again, but I want to choose mu in terms of y only. Sometimes we have to use it in terms of y because this one doesn't work. Again, this is our goal. So we do the same partials of both sides, partial of y on the left, partial of x on the right. So since mu is in terms of y, we have to do the product rule on the left. And since mu is in terms of y, it's treated as a constant over here. We need to solve for this. So factor out the mu. Since we have du, d mu, since we have d mu, dy, because remember u is in terms of y. Factor out the mu on top. Separate. Now we can integrate both sides. And isolate mu, we have to take e of both sides. And there's our formula, mu in terms of y. This is our formula in terms of x. So now let's do an example. So we're going to solve this dE. And it looks like it's the same form as last section. So we're going to check for exact. So using f of x, we're going to just go ahead and find f of y. In terms of y, it's 0. This f of y will take the partial of x. So this is a constant if we're taking it in terms of x. So the derivative of sine of x is cosine of x with that constant in the front. So these are not exact. So in this problem, we're going to just go ahead and try both mu of x and mu of y. So we get practice doing both. So here it is for mu of x first. Mu of x, what's the formula? It's e to the integral m. You guys remember it? There it is. So first, without writing e every single time, we're going to find my minus So remember, we have my here. And this one here is n, and we took it in terms of x, so this is nx. Well, basically, we have f of y equaling to n. We're adding an x. And same with this one. We're adding the y and the y. So our my is 0. Our nx, subtract. And we divide by n. And this is n. And it looks like that cancels with that. And so mu of x so it looks like we'll have to do a u sub, since we can use u because this is mu, but we can use w too. So which is e to the minus integral sine of x is on the bottom. Is our w. Cosine of x dx is our dw. So that looks like natural log. View. And remember, we have to use our power rule before those e and natural log can cancel. So it's e natural log of w to the minus 1. Now they cancel, so this is w to minus 1. We need to backtrack. So now let's go through this. Our new dE take our old one and multiply through by the new mu. So this is my mu. So basically, I'm just going to divide by sine of x.
So that cancels.
So now, this is my new m, which is my f of x. This is my new n, which is my f of y. Is it exact now? We're going to find f of x y, which is my, which is equal to the derivative in terms of y. Looks like it's 0. And then this one, and which is fy. I take x, I take x. And we find that in terms of 0. Oh yes, it's the same. Therefore exact. F is the integral of that. so it looks like it's going to be the natural log of that. If you want to finish it. Which is equal to the natural log of W. So this is the natural log of sine of x plus a constant. But it's going to be in terms of y, since we started with f of x. Derivative. So f of y, I'm taking the derivative in terms of y, but there is no y, so that's 0 plus c prime of y, which is equal to, what is f of y equal to? This is my f of y, it's my new f of y. So c prime of y is equal to 1 plus 2 over y. So now we're going to integrate dy. And so here's our function f of xy. So my solution, okay, that's my f of xy is equal to my constant. Plug that in. And we're done. By the way, maybe you guys saw this already, but when I made my new equation, this one right here, if you look, we could have solved that new equation because it was separable. Would have been easy. Move that over there, integrate both sides, and it turns out to be the same. Okay, so now let's do it the other way. See if we can do it both ways. Sometimes you can, sometimes you can't. The reason why you know that you can't do it is when we find our mu of x, if it ends up being in terms of x and y, you can't do it, okay? Because we said mu of x is going to be in terms of x. Same with mu of y. So mu of y, the formula, so mu of y, we want to find this first. It's our original. M of y is 0, and of x is this. 1 plus 2 over y. Starts with n of x, which is 1 plus 2 over y cosine of x, and that's minus 0, which is gone, all divided by m. M, it's right here, cosine of x. Mu of y, don't forget it's integrating factor, it has e in it. E to the mu of that we just found. And it's dy. Plus plus 2 natural log of y. And so we're going to use our properties here. This is this plus, it's going to be e to the y, e to the 2 natural log of y. And then before we do, cancel e and natural log of y. E to the y, e to the natural log of y squared, which is e to the y times y squared, or y squared in the front looks better, which is my mu of y. It's my integrating factor for mu of y. Take our original dE, which was cosine of x, dx. Multiply 3 by your integrating factor on both sides. And of course, that's still zeros. Go ahead and distribute that. So it looks like these are equal. So we start off with our f of x, our new f of x. Integrate. We're integrating with respect to x. So it's sine of x plus a constant. And since it's in terms of x, this has to be in terms of y. Okay, so now we take the partial in terms of y. It's like we'll have to do the product rule. So we'll just copy the sine of x. It's a constant. But we already know we found f of y right here. So we'll write that out. And it does look like when you distribute that, it is identical. So therefore, c prime of y has to equal to 0. C of y is a constant. So our general solution is this, but c of y is equal to constant. And that comes over there and makes a new constant. So the question of the day, we did this with a mu of x, and we did this a mu of y. Are they the same solution? Here's the other solution that we got. This was from mu of x. This is from mu of y. So we need to check. They certainly don't look identical on appearance. So what I am going to do is I'm going to take this one and raise it to e of both sides. So we do know e to the c is just another constant. So we can say those are equal. Over here, this is e to the power of a bunch of things with a plus. So we can use our exponential properties.
I'm going to just, for simplicity, drop the absolute value. So, this is sine of x, this is e to the y, and we do have to do the power rule here first. This is the same solution. And
Now they look identical. Just a quick question. Not sure I've said this already, but the question is there another way to check if we didn't do it both ways? So let's look at our general solution number 1. So on the right is easy, the derivative of the constant is c. On the left, we can take the derivative term by term. And if we distribute by sine of x, it does look like that is the same d. It'll work for 2 also. You can do it as an exercise. Let's do another example. So we write our given. It's in the right format. Make sure of that. And let's check for exact. So f of yx, so in terms of x, is a minus y there. So be careful. We need to make sure we do these carefully because we need these values in our formula. So let's try mu of x, which is actually e to the integral of y minus nx all over n. But let's just find first my minus nx all over n first to keep it cleaner. So you can see this is m, but we want my right here. So we write minus nx, which is minus a minus y, which is actually plus y, all over just n, which is this, all of that. And we would have to integrate this dx and since it's in terms of x's and y, this is not going to work. There's no partial integrations. So that means we have to use, I told you this might be the case. That's why I give you both formulas. E to the integral of n mx minus my all over m dy, and so to keep it clean we'll just find mx minus my all over m, which is going to be, these terms are going to be flip-flopped, minus y, terms are right there, There's nx, there's my minus that. All over m, which is, this is m. Not as bad as the previous. Not great. So at least we don't have sine of x in there, and we might be able to simplify it to see if it's in terms of at y. So let's simplify it. A lot of y's in common. Down here we have a lot of y's. Actually, let's go ahead and combine these two. So to clean this up, and let's factor it. On the top, we have, we'll take out the negative. Bottom, factor out a y. Oh, how about a y squared? Oh, wow, look at that. That'll go away. So let's continue. So now we can put it in our integral. Which is, that's the natural log with the constant of -3 in there. First power rule of the algebra, because otherwise it's not -3y, that's not the answer. You have to do the power rule first. So now it's y to the -3. That's our integrating factor. Our dE was y squared plus x y to the third dx plus which is 0. There's our dE, our integrating factor. Again, so that means 1 over y to the third, 1 over y to the third, 1 over y to the third, multiply through by your integrating factor. That is what you do with integrating factors in this class. Okay, clean it up. That's 0 on the right. So now let's check for exact. So this is our new m equals f of x. This is our new n equals f of y. So this will be f of xy, which is actually m. We added the y at the end, my. In terms of y, again, that's y to the -1 minus y to the -2, 0. And so f of yx, which is actually n, and this is y, so I add an x on both sides. So basically, just to remind you, we're going x, x. That's how we get that. which is equal to, so this is in terms of x, which zeroes that out, which zeroes that out, so we only have this one term, is the derivative of that, and y is constant. Okay, so it's the same. Therefore, it's exact. Let's start off with our f of x, our new f of x, which is here. F is, what's it called? The integral in terms of x. So it's 1 over yx plus x squared over 2 plus our constant. It's in terms of y. Take the derivative in terms of partial in terms of y.